like I said in class, I'm going to try and keep this lesson short and sweet. But the nice thing about this lesson is that it's really an application of math when it comes to real life, or specifically in physics. So if you're in physics, you've probably already talked about this. If you're not in physics, you're definitely going to talk about this next year when you take it. Okay, but what we're going to talk about today is forces. Okay, forces are something we encounter in everyday life. Think if you're pushing a desk, if you're moving your desk. Okay, when you move something with force, you actually have two separate components. So forces, they have two components. Okay, your two components, the first one is how much oomph you put into pushing that desk. Okay, so that is like the size of the force. All right, and the size of the force, the amount of oomph behind it, is what we call magnitude. Okay, so magnitude is the amount of oomph, the amount of force, or the size of the force that you're putting into moving something. The other component of the force is direction. Okay, it doesn't just matter that I'm moving the desk, it matters if I'm moving it forward, if I'm moving it backwards, if I'm moving it diagonally. Okay, so force has two components, magnitude and direction. And anything that has both magnitude and direction, we call this a vector quantity. Okay, if we take into consideration both the magnitude and the direction, that's called a vector quantity. If we only consider the magnitude, the word for that is a scalar quantity, but that's more of physics. Okay, and when we think about moving something, though, we're applying a force to something, most times we have more than one force. Okay, and for us, I mean, like I said, in physics, you're going to step this up a notch. But for us, we're just going to look at when you have two forces moving on an object. Okay, and a good example of this is if I have an object, I'll put it here, and I'll call it O because I'm so creative. Okay, I can have one person taking this object and pulling it this way. But I can, and I'll call this force 1. Okay, but even though one person is pulling this to the right, I could have another person pulling this way. Okay, what we want to find out is if you have force 1 and you have force 2 pulling this object, where is this object actually going to end up? Okay, and it ends up being that it's going to be right kind of smack dab in the middle, and what we call this is the resultant force. T-A, if I could spell. Okay, we call this the resultant force. It's the force that's a result of the other two forces acting upon this object. Now, if you look, we can actually use some of the geometry that you guys already know, some of the trig that we've learned to figure out what this resultant force is. Okay, because, and this is kind of like the buzz of vectors, whenever we have vectors, a really nice thing is if we put them tip to tail. Oop, not tail, tail. Tip to tail. Okay, so if we take the tip of this first function and we move it so the tail, function, we're going to take the tip of force 1, so where the arrow is, and I'm going to take the tail, or the back end of force 2, and I'm going to put it there. Okay, if you look, what I'm constructing right now is a parallelogram. Okay, so if I took both of these forces and I move them so they're all tip to tail with each other, I get a quadrilateral, that's a parallelogram. Okay, force 2 in black is parallel to force 2 in purple, and force 1 in black is parallel to force 1 in purple. They both have the same length. They're both parallel. Here I have a parallelogram. And really what I want to find is the diagonal of my parallelogram. Okay, and also this diagonal, this resultant force, breaks my parallelogram into a triangle. We just learned all these awesome trig formulas for triangles. Okay, so let's step this up with an example. All right, it's a little lengthy to write, but we'll only do one. Yeah, we'll only do one. Okay, so let's have two forces of 25 and 15 pounds act on an object so that the angle between them, so the angle between the forces, is 75 degrees. Find the magnitude of the resultant to the nearest pound. Ooh, my arm is tired. Okay, so for starters, you know, reading this, I know that I have two forces, so I'm going to have two arrows, and I know that I have an angle between them of 75 degrees, so let's draw the picture. Okay, I'll do the first force of 25 in red. So I've got a force of 25 going this way, and I've got a force of 15 pulling it, so it's 75 degrees between. Now, I'm not going to exactly go 75, but that's going to be somewhere up here. And I should make this vector shorter because 15 is less than 25. And I know that this angle in between here is 75 degrees. Okay, I'm going to go ahead and do some tip to tail with my vectors. So I'm going to take this 15 vector that's in blue, and I'm going to put the end of it at the tip of my 25. So I'm going to make my parallelogram right now. So here's this, and then I'll do the same thing to complete my parallelogram. Definitely not a perfect parallelogram, but whatever. Okay. What I want, my resultant, is going to be this vector right here. Okay, that's my resultant in purple. Okay. Now, I need to use what I know about triangles and parallelograms to figure this out. Okay, now what I'll do is I'll call this side R for resultant. Okay, and I know that this side is 15, and I know that this side is 25. Because if you look at this triangle right here, I'll look at the bottom one. You can look at the top one. I know two of the sides, and I want to find the third side. Okay, so right now we should all be thinking, hey, maybe law of sines, maybe law of cosines. That might help. Okay, the issue with the law of sines is I don't really know if I know enough information to do this. And the law of sines is kind of funky. So I'm going to try and use the law of cosines. So if I know, but in order to use either of those actually, I need to know something about the angles. Right now, all I know is that this big angle right here is 75. Okay, but we should remember two fun things about parallelograms. For starters, opposite angles are congruent. So this big angle over here is 75. This one over here also has to be 75 degrees. Okay, and we also should know Sorry about that. We should also know that if we add up consecutive sides of a parallelogram, they're supplementary. So that means if I add up this angle right here, I'll call that angle A. I know that if I add up angle A, and I'll call this whole one angle B, A plus B should equal 180. Okay, so angles that are next to each other in a parallelogram add up to 180. So I know that angle A has to be 180 minus 75, which gives me 105. So this angle in here has to be 105 degrees. Now I know two sides and the angle in between, so I can use the law of cosines, because that's the criteria for the law of cosines. You need to know two sides and the included angle. So now I can find R. Okay, so R squared is going to be equal to 25 squared plus 15 squared minus 2 times 25 times 15 times the cosine of 105. And then we can go ahead, plug in all of our stuff, and we're going to get some huge long decimal, which I'm not going to go through because I know that we can all pump all of this into our calculator, making sure that you're in degree mode. And when you take the square root, you end up getting that R is about 32. So that is going to be the magnitude of my resultant force, 32. 32 pounds, actually. And that's about it. Okay, so that's how we're going to do all of these vector problems. We're going to take our two forces and we're going to draw them as vectors. So like what I did with this first 25 and the first 15. Then I'm going to move everything tip to tail so I have a parallelogram, because I know that the diagonal of the parallelogram is going to be my resultant. And then I can use some properties that I know about parallelograms to kind of get it so I can use the law of cosines, or if you really want to, the law of sines. Okay, we're going to do more examples in class, but now you actually know a little something about vectors.